Hello, this is Philip Myers of PEMY Consulting. Welcome to Engineering Units for the Plant Engineer. This is Unit 6 on pressure. Let's refresh about pressure units. Pressure, as you know, is force per area, and the dimensions are force per length squared. You should know by now that the Newton is a kilogram meter per second squared. If you divide by meters squared, you end up with units that you should also have memorized, which is the pressure unit in the SI system, kilogram per meter second squared. That has a nickname, the Pascal. And the Pascal is relatively small because 1 atmosphere is 101 pascals. Is 14.7 psia. This is abbreviated 101 kilopascals. In the USCS system, we have to convert feet to inches or inches to feet because we work with two sets of units, pounds per square foot and pounds per square inch, or PSI. The relevant conversion factor, of course, is shown here. A few properties about fluid statics is useful. A static fluid has no shearing force. That means that an object sitting in a fluid cannot exert any force on another object from transference from the liquid. Now, Pascal's law is very useful. It basically says that the pressure acts equally in all directions. The practical translation of that is that the pressure force is always normal to the surface. So if I had a boundary here, the force would be acting normal to that boundary or downward. If I had a boundary like this, it would be acting to the left, and at the top it would be acting up. So this is a useful principle to be aware of. Now, this is probably the most important slide in the whole deck, and what is shown here is a increasing pressure axis going up like that. There are two reference points. The absolute pressure reference is here, and it's set to 0. You cannot have a pressure that is negative in the absolute pressure scale. But there's also an atmospheric pressure scale, which is referenced off of this line. That, of course, you can have a plus or minus pressure, minus representing something below the atmospheric pressure, which would be a vacuum. So this is called pressure absolute, and when you're talking about units in the USCS system, this should be identified by PSI A for absolute. When you're talking about the gauge system, you write PSI gauge. That should always be done. Of course, you don't need to add the A or the G when you're talking about differences in pressure, which is fairly common. Now, pressure here is shown as a constant line, but in reality it's fluctuating like this depending on location, elevation, the weather, and other factors. So it's not a constant, but we assume that it is a constant in standard terms. Now, if you're doing accurate work that requires precise numbers of digits beyond 1 or 2 decimal places, then you need to know what the barometric pressure was at the time of the measurement, or you can have significant errors in your calculations. Now, an important point is that gauge pressure is very common because most of the industrial instrumentation uses differential pressure as the method of recording pressure. Differential means difference of pressures, and the baseline is this atmospheric pressure here. So a simple gauge, most gauges, if you put pressure in here, this tube is filled with an internal pressure P. Because of the curvature and the difference in the radii of the inside and outside edge of the tube, a small amount of hoop tension develops in this outer leg of the tube, and it wants to straighten out. That's pretty intuitively understandable. Through this linkage and mechanisms and this gear, the pressure pointer moves like that. So this pressure gauge is referencing the atmospheric pressure because it's surrounding the sensor. So it's a differential pressure device. Now a few words about fluid statics. If this container has, say, atmospheric pressure here, and this is the liquid surface, we measure H down into the depth of the liquid. A key principle is that at any horizontal line, the pressure is the same everywhere. So it's the same here or here or here or here. That can be proven by considering a mental experiment where you consider something like a tube, a straw. The areas on both ends are equal. The straw is just a membrane. It's infinitely thin, colorless, transparent. But you know that in real life this liquid in equilibrium is not moving around. Therefore, these two forces acting on it at a constant elevation show that the pressure at any given elevation must be a constant. Now we're of course assuming that the thickness of this tube is very small so that the pressure doesn't change much as you increase in depth. Now if you flip the tube into a vertical orientation like this, the pressure at the bottom must be greater than the pressure at the top because it has to support the weight of this liquid in here, and we know that that doesn't move either under equilibrium conditions. Therefore, pressure again is not uniform with H, it's increasing. As we know, it's this formula here. Pressure is equal to the density, the mass density, times the gravitational acceleration times the height, or as I like to generally use, this specific weight, which is the force per unit area times the height of the liquid. This can be derived fairly easily. We'll say that this is just atmospheric pressure or gas pressure. Let's just say that it's all at the same pressure. There actually is a slight gradient because gravity acts on gas just as it does on liquids, but it's small enough to ignore. So the pressure anywhere in this upper space is the same as the pressure at the surface of this liquid. So we'll call that pH0. This is 0.0, this is 0.1, this is 0.2. If we take the difference of, say, pH0, the surface pressure, plus H2, that's the total pressure at 0.2. We subtract off the total pressure at 0.1, you can see that the P0s, the gas pressure above, cancel out, and you're left with pH2 minus pH1 is equal to rho g times the height difference. That makes sense. Now, if we choose this tube to start at the surface of the liquid like that, and we say that the pressure here, P, is equal to 0, psig, then a lot of these values drop out and we're left with pH. The pressure at depth in the liquid is rho gh, or just gamma h. So we've proven the formula that's commonly used, rho gh. Now we need to talk just a minute about barometers. As you already know, the pressure at any 2 points is the same, so these two red dots have the same pressure. If we took a tube and evacuated it and stuck the end into a puddle of liquid, then the liquid would rise, and because we know that this is atmospheric pressure, we can compute H, how high the liquid would go up in the tube. So we have the basic formula, P equals gamma H, or H is equal to P over gamma. If we take atmospheric pressure as 14.7 psi, we can multiply by the square of 12 inches per foot. You can see that the inch square and the inches here will cancel out, and we're going to be left with pounds force per square foot. The pounds force will cancel out, and we're left with units of feet in the top, of course. That calculation's done here, so you can just take these numbers out, manipulate them, and then add the units after you cancel them out. And we end up with 33.9 feet of water. It's water because we used the specific weight of water here, gamma H2O. Now, 34 feet is a tall barometer and is not practical, so people have switched over to a dense liquid, mercury, which has about 845 pounds force per cubic foot. It's very heavy. When you do the same calculation, you end up with 2.5 feet, or in millimeters, using this conversion factor, you end up with 764 millimeters. Now note that this does not equal the 760, which is the sort of the standard measurement of barometers, but that's simply because of the choice of units, and so you always have to be careful about which system you're using. You can see here that a standard atmosphere is 750 here, but in this other system, ISO and NIST, it's 760. So this is critical to watch out for when you need to do accurate calculations, which is generally not the case. Okay, the pressure equipment that we talked about, pressure gauges and relief valves. They're used to protect piping and pressure vessels and so forth. So when high pressure exceeds some value, these will spit out the excess pressure through this piping, which usually goes to atmosphere or another vessel. An important fact about these is that they are also differential pressure devices. They are working the pressure between the fluid pressure at the input and atmospheric pressure measured against a spring internally. There's a hole in this casing that lets the atmospheric pressure act on the other side of the diaphragm, and it's a differential pressure device. So in the next example, I'll show you how you should be aware of this. Here's an example of how understanding or not understanding that relief valves or differential pressure devices can get you into trouble. Many companies require that any place hydrocarbons can be isolated in valves, that they must be relieved by a thermal relief valve. So for example, in this valve, you can block liquid from here to here. And then from this valve to this valve, you could block this liquid. And then similarly for this segment. Notice that each one has a relief valve. The purpose is to dump the pressure to the previous section and ultimately back into the tank where it can reverse flow and relieve the pressure. Now, why is this the case? Well, to understand that, you have to understand the physics of a piece of pipe that has no air in it but is filled with a hydrocarbon. It turns out that there is about an 80 psi per degree Fahrenheit pressure increase. Rate of thermal expansion is greater for the hydrocarbon liquid than it is for the pipe. Now, in many cases, you don't see the effects of this because if there's a small air bubble or a very small leak, that will bleed out the pressure. In fact, packings are notorious for leaking, and it's because of this effect. But good design requires that you protect the pipe and you not let it get above its design pressure. So you can see here what the mistake is. If I set this one at 100 psi, this one will work fine. Every time this section gets above 100, it's going to dump the excess pressure. But here's where we run into problems. I'm setting this one at 100 psi, but unfortunately, it will only open when the line pressure here is 200 psi because the difference here is the delta in pressure is how the device works, not absolute pressure. It's working on differential pressure. Similarly, the pressure in here will be 300 psi when it relieves. So your intent to keep the pressure below 100 has actually resulted in a far excess of your limit of 100 psi. There have been cases where, say this is a 90-degree valve to open to a tank trucker, for example, to tank truck to fill it with gasoline. There are people that have broken their wrist because such a high pressure was in this segment that when they opened the valve, it just slammed open and busted their wrist. So being aware of this is important. It's a safety issue, and I recommend that you put thermal reliefs wherever the liquid can be blocked.